Okay, you can see my my slide. Yeah.
Yes, we can see.
Okay, thank you very much. Yes. Before we start our tutorial, yes, let me know that please, turn off your mic and the video. Your video. I think you can see here the video stop. Yeah, because we want to consider this tutorial will running well. Yes, smoothly. We want to reduce the load of the streaming. Yeah. Okay. And Wahyudi-san will control this tutorial later. Yes, and if you need to turn off, is please mute the participant. Yeah. Okay. For the first is I want to introduce the 7th Asia Pacific Conference on Synthetic Aperture Radar, or APSAR 2021, that will be held in Bali Island, Indonesia, on November 1st until 5th, 2021. Actually, we even in the COVID is we prepare in hybrid conference, online and in-face conference. Yeah, and for the detail, as you can find this on this website, APSAR 2021.org, and we serve also the pre-conference of the APSAR 2021 online tutorial series on synthetic aperture radar from today. Yeah, actually we already start last week, 2 weeks ago. It is under the Indonesian Society of the Remote Sensing, and then from today we start. It is focused for the synthetic aperture radar and other remote sensing technology. And you can find the detail of the schedule and the Zoom and the YouTube link. Yes, from this site. Yes, episode 2021.org/tutorial- series. Yeah, this symposium and this tutorial is sponsored by the IEEE JRSS and also JRSS IFT. IFT is Instrumentation and Future Technology Technical Committee, and where I'm one of the co-leader for especially for the unmanned aerial vehicle technology. And then also sponsored by the Chiba University and IEEE Indonesia section, and then Indonesian Society of Remote Sensing or MAPINS, yeah, and Indonesian Aerospace Agency LAPAN, and also the agency for the assessment and application of the technology, BPPT, and also ITB and some of the Indonesian university. Actually, the this pre-tutorial is a pre-conference. The online tutorial series is we serve many tutorial. At least it's 5 tutorial in 2 weeks, every 2 weeks. Yes, and then today the presenter is myself. I'm Josaphat Tetuko Sumantyo from Chiba University, and also from the Universitas 11 Maret Indonesia. Today I want to serve the basic of the synthetic aperture radar, and then gradually another professor will explain to you about the detail of this technology of the synthetic aperture radar, image processing, and also the some application. And next, the second is Professor Yoshio Yamaguchi, the emeritus professor from the Niigata University, Japan. He will talk about the polarimetric, and then Professor Hongbo from the Singapore, yeah, the Agency for the Science, Technology, and Research. he will talk about the radar, yes, for the drone. Yeah. Okay. And the symposium itself, the episode you can see here. We serve many sessions, and I hope you could attend this symposium. We serve many sessions that cover almost whole of the aspect of the synthetic aperture radar, or SAR, and we also serve some special session. If you want to create the special session, please ask me, yes, or send to the email. You can find the email on the website of the episode 2021. And we also have some award. Yes, it is. I think it's very interesting award. Yes, especially in the best paper award, best student award, PolSAR award, and we also consider another award. Yes, and now we also creating some competition, and you can find I hope next month, yeah, open by the IEEE GRSS. It is in the technology of remote sensing, yes, for the UAV. I hope you can also join this competition, and we will review and make some selection, and we will decide the winner and give the award in the opening ceremony of this episode 2021. Yeah. Okay, in the deadline of the abstract, you can find here. This is April 30. We still have about more than 1 month, yes, and then the paper submission is May 21, and yes, after the notification, registration, and the final paper in September 1st. We have plenty of time. Please prepare to submit this symposium. And you know, we also consider, especially from the Indonesian participant, with the good price for the registration fee. Please, join us, and then we promote the technology of the synthetic aperture radar. Yeah. Okay, I want to start my wait a minute. Yeah. This is as in the title here, the synthetic aperture radar, or SAR. Yes, it is especially I want to focus on the basic of the synthetic aperture radar. It is in the image signal processing, yes, and the application. You can find it is the radar that I developed, that already installed on the UAV and the microsatellite, and also the this aircraft, especially the CN235 MPA. I think it's Indonesian guy is know well about this aircraft. Yeah. Okay, it is my biography. Yes, it is a short biography from the bachelor, master, and I study at Kanazawa University, and then from the PhD at Chiba University. After that is I'm to be the lecturer, associate professor, and full professor in Center for Environmental of Remote Sensing, Chiba University, and also at the Department of Electrical Engineering of the 11 Maret University of Indonesia. And actually, I'm also a visiting professor in 13 university in Indonesia. Okay, because the time is not so much, as I want to talk fastly. Yeah, this is first is I want to talk about the characteristic and the history of the synthetic aperture radar. Yeah, first is the introduction. Yes, like you know, the synthetic aperture radar, or SAR, it is the satellite from the platform. Yes, even the satellite, aircraft, and then the UAV. We install the synthetic aperture radar system, and then illuminates the microwave, and then scattered. After that, the receive the back scattered wave, and then process it to be the image. Yeah, because working by transmit and receive. And it is we call in the active. So sometimes it's the synthetic aperture radar called in the active sensor, and then the sensor is have the to make the image, yes, or to form the imaging. Sometimes it's also called as the imaging radar, yeah. And because this radar is transmit and receive by themselves, so it means it is the active. So sometimes it's called with the active sensor or this microwave, because using the microwave we call also as the microwave sensor. And then different with another radar. The synthetic aperture radar is put and then transmit side looking. So on the side, yes. If the aircraft is moving, yes. Okay, I have to. Okay, for example, it is the aircraft. Yeah, we put the radar is here, and then we, when the aircraft is moving, and then transmit, yes, and then receive. Yeah, it is we put on the side. Yes, so we call as the this radar also on the side looking radar. Yeah, and the benefit of the synthetic aperture radar because working in in microwave, you can see here. This radar is working in from the P band, L, S, C, X, K, Ku. So actually, commonly is use the P band, L, S, C, X. Sometimes it's Ku or Ka. Yeah, but from the satellite is used the L, C, X is common. Yeah, sometimes it's S band. Yeah, because if you see here, it is in the atmospheric penetration ratio. You can find here it is 100% penetrate. It means from the P band until here, Ku band is can penetrate the cloud. Yeah, it means it is we can use this sensor in any weather. So we call as the all weather sensor. Yeah, and because it is active sensor, different with the optic sensor. Optic sensor with the source is from the sunlight. Yes, it means depend on the sun itself. Yes, in the nighttime you cannot use the camera on the optic sensor, but the synthetic aperture radar, even the nighttime, you can operate and then transmit and then receive in the nighttime. So we call this sensor also the day-night sensor monitoring on the active sensor. And because we transmit the pulse that we call also the chirp pulse. Yeah, if the sensor itself, after transmit and scatter and receive, you can get the receive signal, and then you compare with the pulse that you already know. It is the chirp pulse. Yeah, and then because the transmit and also the receive one, it means you can get this image with the high coherency. Yeah, it is the information from the phase itself. Yeah, from the phase information you can derive using the interferometric synthetic aperture radar or INSAR, and then differential interferometric SAR, the INSAR, and also the permanent scatter on the persistent scatter interferometric SAR on the PS INSAR, and so on. Yeah, you can use this phase information for your application. Yeah. Okay, next is the polarization. Next is the second tutorial is by Professor Yamaguchi. He will talk more about the polarization, and he is famous, very famous for the polarimetric SAR. Yeah. Okay. It is in the polarization. The information of the polarization also very important. So you can employ this polarization information for the polarimetric SAR. And in my case, is I developed the circularly polarized synthetic aperture radar, and you can read the newest paper last December. Yeah. Okay, but the weakness, it is the interpretation is very difficult. Yes, because it is working in microwave. You cannot see by using your eyes. It is you can, but it's no problem if you learn about the electromagnetics and wave scattering or wave propagation. And I think you can make the some modeling and then analyze wave of the synthetic aperture radar, and some distortion. It means because we transmit side looking. It means the near range and also the far range. Yes, will happen on your image. It means it is made some distortion. We call as the foreshortening, shadowing, and sometimes is layover. Yeah. Okay. In this case is when you want to process the image processing of the synthetic aperture radar, at least is you must know three. Yes, it is the intensity of the the wave. You can derive from the later as we call in the backscattering coefficient, and then the phase itself. It is for next is for the INSAR, the INSAR, PS INSAR, and polarization. Yes. Okay. Please remember just three most important information from the image of the synthetic aperture radar. Okay, and the characteristic is like I already talked. It is the SAR image is free of the cloud, and then the haze, and also sometimes is the the fog. Yes, and the mist. Yes, because use the microwave and can penetrate. For example, this is one when I analyze of the fire burn at the Central of Borneo, and you can read my paper in International Journal of Remote Sensing. It is when I'm a PhD, and then the phase itself. It is one application is I observe the land subsidence of the Bandung city. It is my hometown at Bandung city of Indonesia, and you can read the technique is in this IEEE TGRS. Yes. Okay. Next is the intensity itself. It is in the optic. And next is it is in the synthetic aperture radar. The optic is it's very easy because your eyes is can know about the scattering of the wave from the sun and then scattered by the Earth surface. Yeah, it is just the surface. Yeah, but the synthetic aperture radar is can from the intensity information. It's not just the surface, but you can also find the underground information. Yeah, it is for example, it is the boundary of the Egypt and I think Somalia. Yeah, it is when we analyze about the underground under river. Yeah, it is you can find the water even in the desert area. Yeah, I think you can implement this technique is for many other application. Yeah. Okay. Next is the characteristics of this synthetic aperture radar or SAR and the optic sensor you can find here. Yes, optic sensor is very easy because your eyes is can know familiar with the scattering from the sunlight. Yes, and easy to understanding. Yeah, but SAR has cannot because the wavelength is long. Yes, so your eyes is cannot recognize the wave. It is difficult to understanding. Wavelength is in order a centimeter or meter. Yeah, and then the mechanism is complicated and distortion. Yes, it is I already talked. Yeah, it is one of the image from my circularly polarized synthetic aperture radar that we flew at Indonesia. It is south of the Celebes. It is the close to the Hasanuddin airport. Yes, it is when we flew. It is the optic sensor and it is our synthetic aperture radar. It is the cloud. It's covered by the cloud. You don't know about the the information of the Earth surface, but using the synthetic aperture, you can find it's very clear. Yes, for the details you can read in my paper here. Yes, last December is published in IEEE JSTAR. Yeah, it is you can find about the theory of the synthetic aperture of circularly polarized polarization and also some application. Yes, I hope you can continue this this research. Yes, please consider some application using this CPSAR. We call it the CPSAR, a circularly polarized synthetic aperture. And from next April, our Center for Environmental Remote Sensing of Chiba University will open of this CPSAR images. Yeah, please also you can apply for the collaboration with our center, or especially with our laboratory, to employ this CPSAR images. And we will open gradually our heritage of this CPSAR images. Okay, next is the history of the synthetic aperture radar. You can find here, this synthetic aperture radar is have the long history. Yeah, you can see here, started by the Carl Wiley, yes, from the Goodyear Corporation. He invented the synthetic aperture radar in 1953. After that is this technique is used for the civil application, for example, the archaeology, using the real aperture of the interferometry. And then after that is for the spaceborne SAR. Yeah, it is the America launched the CSAT. This is in 1978. This is when I'm 8 years old. Yeah, it is the first one. Is with the resolution is 25 meter. Yeah. After that is the Russia. Yes, launched ALMAX in 1980s. Yeah, and then America also launched the space shuttle imaging radar, or SIR. Yes, it is by the NASA. And then from the civil spaceborne mission, it is 1991. It is in the ERS-1. I think it's Earth Resources Observation Satellite. Yes, first. Yeah. Other that is ERS-2 is also launched. Yeah. And next is Japan launched JERS-1. Yes, Japanese Earth Resources Observation Satellite, or JERS-1. It is with resolution is 12.5 meter resolution. And next is RadarSat, SRTM, NVSat. I think you familiar with the name of the ELOS. Yeah. And next TerraSAR X. Yes, I think you also already familiar, especially some student right now I think is familiar with this what is spaceborne mission. Next is the ELOS-2 and Sentinel-1A, 1B. It is especially Sentinel-1A, 1B is free of charge. It is I think is a good opportunity for the student and young scientists to employ this this images of the satellite to to observe your environment. Okay, in the history of the SAR imaging technique, it is firstly is we use the it is optical processing method, because last in 1960 it is the analog. Yeah, analog technology is in this time. Yeah, after that is from 1970. Yes, it is when I born. Yes, it is already the digital processing of the SAR images. And next, 1980, it is from the optical processing is then moved to the digital processing. But in 1990s, the Russia is still a hybrid, yeah, using the optical processing and the digital. But right now in 20s, yes, especially in 2010s, yeah, it is we almost of the processing is the digital processing. Today, I want to talk you about the digital processing, about how to process the synthetic aperture image, especially from the raw data. Yeah. Okay, this is the first image of the CSAT satellite. In the left side, it is the raw data. Yeah, you can find some, look like the it is curve like this one. Yeah, it is the characteristic of the raw data. And then after you process the range compression and azimuth compression, is you can get this image. It is the image I think is around the California. Yeah. Okay, and This is just for the your knowledge. Yeah, it is in the spaceborne history. Yes, the CSAT, ALMAX, ERS, yes, and then TerraSAR X. But next is also the ELOS and Sentinel. Yeah, and you can find here the polarization is H is means the horizontal and V is the vertical. It is very important for the polarimetric SAR. Yes, you must know about this polarization. And then another one is you need to know about the what is the frequency. Yeah, you can see here the frequency. Yes, 1.275. It is in the CSAT, JERS1, ELOS. It is in the L band. Yeah, L band. Yeah, and then 3 gigahertz. Yes, it is in ALMAX. It is S band. Yeah, and then 5.3. Yeah, 5.3 of the ERS1 radar sat and NVSAT. It is in the C band. Yeah, another one is 9.65. It is in the X band. Yeah, please when you consider the process the synthetic aperture image, please consider the at least in the frequency and also the polarization. Yeah, because it is you can find later in the characteristic of the scattering of the object on the on the ground. Yeah. Next, the airborne SAR. I think it's many airborne SAR in the world. Yes. You can find here. It is some the Germany DRR and JPL of NASA, and also Intermap is America, and also Onera, France, and Japan here. It is the Mitsubishi Electric. It is for the JAXA and ICT. And Canada, Netherlands, and also it is GMRSL. It is my SAR, airborne SAR. Yeah, you can find. I think it's in the website of my laboratory or GMRSL. Okay, and the observation mode. Yeah, observation mode is many observation mode of the synthetic aperture radar. But I want to show you about some what is important mode. Yeah, first in the strip map mode. Yeah, you can see here in the strip map mode is when the we put the radar on the side, on the side of the platform, for example this aircraft, and then move and transmit, receive, transmit, receive. Yeah, and then you process the data later. Yes, it is it is you can see here when moving is the antenna is look like to be very big. Yeah, I think you know about the characteristic of the antenna. The antenna is very large antenna and the beam is small. Yeah, but the antenna is small. It means the beam is very broad. It's very big. One of the the objective of the synthetic aperture radar is to increase the resolution. Synthetic aperture. Yes, synthetic is means synthesize. Yes, to make the man-made of the the antenna, because the antenna itself is very small. It is just 12 meter, but if you move and transmit with the with the length is almost same. Yes, it is you can make like it is the synthetic of the antenna. Yeah, it means you can make a very long antenna. For example, it is using the 12 meter of the antenna, you can make look like the antenna with the length is around 14 kilometer. If the antenna is 14 kilometer, if the beam is to be 1 degree. 1 degree is means sorry, it's not 1 degree. One antenna is to be around 14 kilometer if one antenna. But if you use the 14 kilometer of the antenna, you can get the beam here is to be around 60 meter. Sorry, 6 meter on the ground. It means it's very good. It's very good resolution compare one antenna. So why we consider the synthetic aperture radar? Yes, because we want to make the ground resolution is to be better. Yeah, from 14 kilometer to be 6 meter. You know, I think you choose the 6 meter, yes, compared to the 14 kilometer. But you need to consider about some characteristic of the side-looking radar. For example, here from the side, yes, you can, here is we call in the near range, and here is far range. It is the observation area. Yes, if you want to make the image, yes, you must consider about this the angle, yes, on the off nadir angle, and also this one, yes, we call in the Doppler, yeah, Doppler line, yes, it is in the Doppler. Sorry, it is in Japanese. Because you must consider the Doppler line is must be same. So why we consider the side looking? Because in the side looking direction, it is the Doppler frequency almost same. Yes. Okay. Next is the screen mode. Yeah, the screen mode is when you move this the SAR on the platform, and you turn, yes, rotate the beam of your antenna or your your SAR sensor. So in this case is we want to avoid the shadow, the shadow phenomena of the target. For example, you move like this one, yes, when your platform at the B, yeah, it is in the forward, yes, it is you can get the forward information, but unfortunately if some object, if some object like this one, you observe like this one, yeah, you can get the information here, but unfortunately you cannot find this information on the back. It means the shadowing, yeah, the shadowing. So how to avoid this one is after you observe here and move here, and then you must observe the shadowing area. So in this case, it says better you choose the screen mode. Yeah, you can avoid the shadowing or reduce the shadow phenomena. And then the spotlight mode. Yeah, the spotlight mode is when you move, yes, and you observe the same place. Yeah, if you observe the same place, yes, it means you can increase the SN, yes, signal to noise ratio, and you can get this information is more than the strip map on the screen mode. Yeah, it means you can realize the image with the resolution is almost same to the wavelength. For example, L-band wavelength is 24 centimeter. You can get 24 centimeter of the resolution, and C-band, yes, 5 centimeter, and then X-band about 1 or 2 centimeter. It is if you want to get the high resolution, is please use this spotlight mode. And then here in the inverse mode, yes, if you want to observe the the moving object, yeah, the drone or the shape, yes, you can put this your synthetic aperture radar is fixed, and then the the object is moving close to the front of the your radar, and then you can process it to be the inverse SAR, yeah, or ISAR. And then scan SAR. Scan SAR is it is you observe first here, and then when you move here, and then you observe this area L2, and then move here, you observe L3, and next when you move here, you observe this area, and next this area, and next, it is actually it in the advance of the strip map mode, yeah, but you move like that. You can move this of nadir angle using the mechanical or like the phase array antenna. Yeah, you can just change or move. Yeah, 1 degree every 1 degree. Yes, it is also enough. And you can get the coverage is 3 times of the common of the strip map. But unfortunately, the resolution is to be dropped, but you can get a very large area. And then burst mode. Burst mode is for observation of the like the deep space mission, yeah, because the energy is not so many, yes, and then you know, you need to save the power of your platform on the satellite. Yes, it means, you know, for example, you want to observe this area, is you observe, it is in the black time, yeah, and then the white this period is, it is take a rest, yeah, and then observe again, take a rest, and then observe again. You can get, it's very long, yeah. It is almost same with the ScanSAR. Yeah, the resolution is not so good, but yeah, you can get is long, you know, in what is in azimuth direction, long of the observation area. One of the example is Magellan's mission. Yes, it is the mission for example, here is from the Venus. Yeah, I think you know the Venus is almost every day covered by the cloud. So you need this synthetic aperture data to observe this planet. Yeah, and it is one of the example from, you can find more detail in the NASA website. Next is the wave mode. Wave mode is we want to observe, you know, the area is very large area. For example, the ocean area. Yeah, you observe, take a rest, observe, take a rest. With the, you know, this period is on the distance is 200 to 300, and then you can make the, you know, the average of this area. Okay, next is the image signal processing. Yeah. Image signal processing is many technique. Is first is the spectrum analysis method, GRAM method. It in the I think it's very famous. And next the correlation technique. Yeah, but correlation technique is frequency domain and time domain. But we want to focus on the time domain. It is more easier for us, yeah, to know about the process of the SAR image processing. The time domain is a two-dimension algorithm. And another is the, I think the most famous algorithm we call, and the range Doppler algorithm, or RDA. I want to talk about the RDA. Yeah. First, you must know about the, you know, the geometry of this SAR processing. You know, it is we call in the platform direction. It is the antenna, and then one is the off nadir angle, sometimes also the look angle. Yeah, and then two is the depression angle. If you are military, I think it's you familiar with the depression angle compared to the off nadir angle. But I think it's better you familiar with the one. Yes, it is the off nadir angle or the look angle. And next, here is the near range. Here near range, far range, and also the beam. Yes, it is the beam at the range beam. It is also very important. And then the azimuth. Yes, azimuth beam itself, the 5. Yeah. Okay, it is this beam width is depend on the antenna size. Yeah, like I mentioned that antenna size is big, the beam is to be small. But antenna size is small, the beam is to be large. Yeah. Okay, this is some of the antenna. Yes, and this is the antenna of the JERS1. And then please remember the JERS1 is the length is around 12 meter and the width is about 2.2 meter. And then it is the antenna from the PolSAR, and it is in the antenna of my CPSAR, yes, circularly polarized synthetic aperture radar. Okay, at least yes, you must know about the radar equation. You can see here, yeah, you transmit power is PT after the transmit, and then, you know, it is the distance of the object, for example, R, and you can get the, you know, the power that receive in this, the surface of the scatter, and the gain of the antenna is G, for example. You can get the power here is to be PT times with the G divided by the 4 pi R squared. Yeah, and then scatter again, back scatter, yes, and go back to the antenna, and then will receive by the antenna with the scattered power is to be PT times G, and then the sigma. Sigma is radar cross section of the surface of the object. Yes, okay, and then divide by 4 pi R2, and finally you can get, you know, the receive power is to be this one. Yeah. You can get more information for detail from this, this paper. 1978, it is the launch of the CSAT satellite. Yeah. Okay. When you consider or design the synthetic aperture radar, you must know some parameter. Yes. To know how to design, and every parameter will have correlation with the letter of the image that you want to get. Yeah, it is especially in the SN. Yeah, signal to noise ratio. It is letter is depend on the range resolution, sweat width, and azimuth resolution, and it is have the relation to the antenna size and also the power itself. Yes, the power of the SAR system itself, and also the pulse. Yeah, chirp pulse and the number of the chirp pulse itself. Okay, the radar pulse itself. Yes, it is when we transmit the chirp pulse. Yeah, you transmit and then scatter. For example, it is scattered from the tree, house, and the concrete. Yeah, and you want to observe this area. It is from the near range to far range. You need the time like this one. Yeah, the time of the transmit, scatter to the near range and go back, yeah, and receive, and then transmit to the far range and go back, and then you can get. Yeah, the time you need is this one. Yes, it is very important when you process the images. Okay, next is to process is we need at least is two. It is range compression and azimuth compression. Yeah, and between the range compression and azimuth compression, you need the turn corner turn. Yes, this is just some tricky to process because you need the FFT, yeah, fast Fourier transform. Please learn about the fast Fourier transform and the inverse fast Fourier transform, or IFFT, yeah, when you want to process the synthetic aperture radar images. Okay, why we need to use the chirp pulse? Yes, because if you use the common cosine or sine pulse, yes, with the square, I think you can get the bandwidth is 1 divided by the tau. Yes, it is the length of the pulse, and then using this information, you can get the resolution is to be c tau divided by 2, and tau itself is to be 1 divided by bandwidth b. You can get this the ground the resolution it in the slant range direction to be like this one, but we need to increase the delta r. Increase is mean the resolution to increase. It means the delta is to be more smaller. Yeah, it means you need to control this bandwidth. So in this case, is you need to modify the pulse itself. It is using one of the technique in the chirp pulse. Let's consider. I think many technique to to define the chopper on the pulse. Yeah, I hope you can continue this also on the research of the pulse itself. By using this one substitute here, and you can get delta r equal to the c in the speed of the wave. Yes, it divided by 2 delta f. If you can control delta f, yeah, increase the delta f means to reduce the delta r. Yeah, it means why the concept on the chirpers is I think the excellent idea to realize a good resolution of the synthetic aperture radar. It is one of the example of the JERS one. Yeah, the center frequency 1.275 gigahertz, and the delta f is 15 megahertz, and then the time, yes, this time is 35 microsecond. Yeah, and I simulated is like this one. Yeah. Okay, after you get the scattering, yes, for example, from A, B, C, yeah, it means it is difficult when you use the conventional technique. Yeah, it means when you you can see this this response like this one is you cannot split it or this what is classify it is scattering from A or from B or from C. We don't know. Yeah, but using the chirp pulse, yes, even is mixed but you can use the reference signal and then make the convolution and like this, this equation, and then you can get the response like this one. So it is more clear compared to this one. Yeah, we call it is to be the compression. Yeah, range compression and azimuth compression is actually basically from this technique. Yeah, and then you can get this. The scattering is very clear scattering like this one. Okay. If we employ to calculate this one is for the chairs one, and you can get this the slant range resolution is 10 meter, but on the ground is 17.4, and you can get the product, the official product on the chairs one is 18 meter because based on this calculation. Okay, all this one is why we need to process using the FFT, because if you use process in time domain is it is integral. It means you need to consider the sigma. Sigma is mean the summation. Yeah, summation is depend on the on the resampling time itself. But if you consider process in frequency domain using the FFT, after FFT this equation, you can get is just one time. Yes, one multiplication. It means it is more more efficient of the calculation. Okay, next is the azimuth compression itself. And consider upon the Earth rotation, and then you can get it is the reference function of this when you consider for the azimuth compression. For the detail, I think you can get from some books about the raw data calculation. I want to skip that. You can consider, oh, this one is for the reference function, and then if you compare the reference function of the azimuth and the range, and you can get is same, almost same. Yeah, then you can use just I'm familiar with the Fortran, so why I use made the subroutine for this from the azimuth and from the range compression. Just use one subroutine, it is finished. Yeah. Okay, next, another one is you must consider about the range migration. It is the range migration is itself is composed by the range walk and range curvature. You can get this in the raw data image, you can find some response like this one. Actually, this one is the response from one point, yes, one object that it is composed by the range walk and range curvature. So why you need to make the correction? Yes, after you process the the range compression, and then in the azimuth compression, you need to make the this range migration correction. The process itself is first is you need to calculate this R, and it is move in the azimuth, calculate the R, and then derive the R itself. You can find it is the function of the speed of the your platform and the distance to the center of the Earth, yeah, and the speed of the Earth, the planet itself. If you process from this Earth, it means the speed of the Earth. Yeah, even the speed of the Earth and the equator and in the pole, yeah, North Pole on the South Pole is different. So you must consider, yeah, the speed is different. Yeah, and if you want to observe in the Venus or Mars, you must consider the the speed of this another planets. Yeah. And yes, and the process is like this one. Yes, after you made this one, and then use the the strike, yes, line, and then you made calculation, compression in the azimuth, like when you process at the range direction. Okay, and finally in the multi-look, it is actually multi-look is also another technique to get a good SN, yes, to increase the signal to noise. It means to reduce the noise itself by using the multi-loop. I think some students are already familiar about how to process the multi-loop itself. Okay, we have around 7 minutes. I want to talk about the application. Yeah, I already mentioned you that the synthetic aperture radar image, you can get the information of the intensity, phase, and the polarization. Yeah, first is the phase itself. Yes, from the phase you can process the coherency. You know, SAR have the good coherency. It means you can also use the information of the coherency using the coherency analysis. Yeah, one of the technique like this one. Yes, it is you can calculate. Yes, it is for example two image. Yes, image 1 and image 2. Yeah, it is you can calculate the convolution. Yes, it is what is the complex convolution. Yeah, it is from image 1 and the convolution, and then image 2 and the conjugate of the image 2. Yeah, and you know the square root. Yeah, and then it is the image 1 and the conjugate of image 2, and then you can get the coherency information. And it is I employ to observe the what is it is the earthquake and the Central Java, because my house is I have the house close to this Prambanan, yeah, and two houses destroyed by this earthquake. And then I made the analysis, and you can find, you know, when the building, you know, destroy, it means the scattering from the, you know, emit when the building existed and after, you know, the earthquake and to be destroyed, the distance is different and the scattering is different. So, and then you will find this value will change. It means from the coherency you can get which area is destroyed and which area is stable. Yes, the red one is destroyed. Yes, and then another area is almost stable. And I made the what is some ground survey here, and you can find one paper related to this one. Next, the phase information. Phase information, for example, here from the interferometric. Interferometric is a long track and cross track. If the two, for example, two platform, two aircraft or two UAV or two the satellite moving and transmit and then receive together. Yeah, and then it is you can use this two image to process and using the interferometric and then to derive the digital elevation model or DEM. Another one is differential interferometric. Yeah, and cross track. For example, the the planet and the spaceborne is move, circulate, and then observe one place, and then after that a couple days later we'll observe again, and different time. It means it is the cross-track interferometric. This cross-track interferometric you can process to get the GEM and differential interferometric, or if you observe many times, more than 15 times, and then you can process, to change, to find the change of the Earth surface. We call it is the technique is permanent on the persistent scatter interferometric SAR, or PS INSAR. Okay, it is in the technique of the INSAR. You can get more detail in my paper in IEEE TGRS, yeah, about this technique. You observe, for example, this area. One time is this the surface is at here, but after that, after the, for example, the earthquake on the subsidence on the or what is the volcanic eruption, the surface is to be changed. For example, to be changed to be the DZ, yeah, to be the DZ. If you enlarge, it to be like this one, and you can find the change at the this direction. Or if you want to know about the surface, is the change in the surface, is you can derive the dx and also the dz. Yes, you can get from the change of the information here, the phase information. Yeah, after you derive and you can get the change at the surface. Yeah, horizontally on the vertically. Yes, dx or dz. Yeah, but sometimes somebody also process from the azimuth direction. But at least you can derive the dx and dz direction. Okay, how to process using the synthetic aperture data? For example, I use the master and slave. Yes, master is it is 2007 February 19, and the slave is 2006 May 19. It is the area of the Lapindo. Lapindo and the Sidoarjo is of the Java. Yeah, is Java island. Yeah, after you get this 2 SLC single loop complex of the image, yeah, and then you geometric correction, yes, using the some GCV, and then you calculate, yes, it is in the complex conjugate. Yes, one is the this after the geometric corrected, and then it is the complex conjugate, and then you multiply and you can get the fringing, yes, of the interferogram. And then, but unfortunately in this image it still have the information of the orbit, yes, of the satellite itself. So you need to reduce the orbit information. Orbit information, when the satellite is moving, is you transmit and then receive every, pulse. Yeah, it is have the phase change. You can see like this one. Yes, it is the simulated orbit pattern. You can get, using the existing simulated using the existing DM. After that, you can substitute, yes, from this fringing interferogram using the simulated orbit, and you can get, it is the orbit pattern eliminated interferogram. Yeah, and it is you can find on the ground change. Yeah, and then using the simulated DM, for example, SRTM or GDM or another. Yeah. And Indonesia, I think, also have the RBI, yes, Peta Rupa Bumi of the Indonesia. You can get and simulate it, and then you can compare this one. If you compare and if not so many change, you can use this information to be in the digital elevation model. Yeah, but if you reduce, yes, for example, two of the fringing, and then you reduce, and you can get the change. We call it is the pattern of deformation or phase error of the deformation. It is we call in the D-INSAR. Yeah, and then after you made the unwrapping, yes, and you can get the real change of the lens substrate surface change. Yeah, we call it is the pattern of deformation, real deformation. Yeah, it is one of the D-INSAR. And then it is one example when I employed for the Jakarta city. And finally, it is if you use many of the INSAR interferogram images, yes, and you process and you make the average of this change, you can get, the average of the change. It is the Bandung city change. You can find the lens subsidence, the speed of the lens subsidence at the Cimahi city, and it is in the Dayakolot area. And yes, my house is around here. Yeah, you can get, the average every year is how many centimeter or millimeter change you can use to predict the disaster in this city. And the polarimetric SAR, actually Professor Yamaguchi will talk more detail later, but it is one example. Using, polarimetric SAR, you can derive the surface scattering, double bounce, and volume scattering. You can use this technique. Yeah, I think you can find the PolSAR Pro. Yes, it is one of the free of charge software to process the polarimetric SAR, and you can get the image like this one. It is one of example of the Surabaya. It is double bounce in scattering from the urban area. So you can find this is the building scattering from the building, and then the surface scattering from the flat body. Yeah, it is from the sea, lake, from here is, for example, it is from the, I think is what is in Indonesia is tambak. Yeah. Another one, it is land subsidence of the Lapindo. Yes, also we can observe. Yeah. Okay, and the volume scattering is from the tree. Yes, it is from the multi-scattering. You can use to extract the tree on the biomass using the polarimetric SAR. Another one is in the Toba Lake. Yes, it is very beautiful. Yeah, I think you can employ this polarimetric SAR to derive, the information, and then you can employ to make the map. Yeah, comparing the optic sensor, I think this is delineation is more easier. Yeah. Okay, finally, I want to close my my tutorial, and please consider to join the Aperture 2021 that will be held in Bali. Yes, on 1st until 5th of November 2021. Yeah, please check to this website, and then at least please submit the abstract as soon as possible so we can consider for you later. And okay, thank you very much, and waiting you in episode 2021. Yeah, thank you. Yeah. Next, Professor Yamaguchi. Yes, yeah. I will deliver the time for you. Yes, thank you very much. Yeah.
Thank you. Yeah. Thank you for a nice presentation.
Yeah.
Just a moment. Okay. Okay, can you see my slide?
Yes, Sensei.
Okay, yes, yeah. No problem.
May I start? May I start my presentation?
Oh, sorry, noise disappear.
Noise, no noise.
No, disappear. I don't know. Other people can see the slide?
Very sorry, we couldn't see the slide, sir.
Okay. How about this?
Okay, no problem. Yes, we can see. Yeah.
Is it okay? Is this okay?
Okay, no problem. Yeah.
Okay. Yeah. Then I will use this slide. Now, hello, everyone. Welcome to Aperture tutorial. As you know, this pre-conference is scheduled by Professor Josaphat. As in this previous presentation, he's very active and energetic and very powerful professor. I respect him. I was invited to present tutorial in this session. Yes, I was delighted to answer and accept his proposal. It is my pleasure to serve his purpose as well as for the success of Aperture. Following his enthusiastic presentation, I would like to present PolSAR imaging by scattering power decomposition. I am Yoshio Yamaguchi of Niigata University, a little bit old, I'm retired now. But I will try to explain this topic in an easy way as much as possible. So my presentation is like this today. First, in introduction, I will show important concepts of polarimetric radar. And scattering matrix is a basic quantity of polarimetric radar. Using scattering metrics, we can develop polarization matrices such as covariance or coherency, Keno-Muller matrices. But in these matrices, there are 9 independent polarization parameters. The number is much more than single polarization or dual polarization radar. We can use it. One way to utilize these parameters are scattering power decomposition. In section 2, I will show some procedure of scattering power decomposition based on the experimental evidences. And the power is a basic quantity. If we use color for each scattering power, it's possible to create full color image, which are easy to understand for everybody. In section 3, last part, I will show several examples of Eros PolSAR image as well as airborne PolSAR image. Okay. Now, this is a tutorial. I will begin with electromagnetic wave. Many of you know electromagnetic wave, but we cannot see it. We cannot see electromagnetic wave, radio wave, microwave. But think about what happens if it is seen. How can utilize it? This is a starting point of my interest. Because electromagnetic wave, radar wave has advantages. Penetration of clouds, penetration of forest for L-band. It works under any weather condition. Day and nighttime operation is possible. This is already mentioned by Professor Josaphat. This is a great advantage. When we took flight, this picture was taken from airplane. As you can see, we can see the many clouds, white clouds, but we cannot see beneath the cloud. Radar wave can penetrate. Just comparison of optical image versus radar image is shown here. Upper one is Google Earth optical image of volcano mountain Bromo in Indonesia. The lower one is Eros PolSAR image. Just compare. In the upper optical image, there are white area and smoke here. We cannot see underneath, but for radar wave, nothing. We can see directly the surface of the mountain slope. This tells everything. Radar is all weather, day and night, vast area, simultaneous measurement. This is great advantage. In addition to radar sensing, here is polarization. Polarimetric radar is described here. We have transmitter, 2 transmitter, H polarization antenna and V polarization antenna here. Downwards is a reception and receiving antenna. For example, if we transmit horizontally polarized wave, electric field is in this way, line. It is transmitted from this antenna and hits object and returns back. The polarization state is not identical with horizontal one, usually elliptically polarized. This wave can be constructed by the combination of HH component and HV component. We have two reflection coefficients here, complex values. So first we transmit H polarized wave and receive H and V polarization channel. Then we switch from H to V for transmission and receive the same simultaneous measurement. In this way, we have 2 by 2 polarization combination reflection coefficient. This S is called scattering matrix. This is a basic quantity of polarimetric radar. Let's take an example. We have HH, HV, VH, VV channel coefficient. Suppose we have objects like this. Here, red one is dihedral, a 90-degree oriented diplane, two planes, oriented in this way and in this horizontal way, and oriented dihedrals here. And green one is flat plate. Yellow one is corrugated wire here. H is in this direction, V is in this direction. SHH image becomes like this, SAR image becomes like this. Strongest comes from here, dihedral, biggest dihedral, and this red comes from this dihedral. Green comes from this flat plate, but we cannot see oriented dipoles here and here, and no echo from here. But in VV image, we have echo from here. This is reflected from wire structure. No echo from oriented dihedrals. But in HV image, we see clearly this oriented dihedral echo. From here, we can understand. If we use single polarization, we miss the information from here, here, and here. Here and here. And HV, only 2 points appears. By using all combination, we get all information on this object. This is a scattering matrix. Now, lots of space-borne polarimetric SAR system is orbiting in space. Eros 2. Here, as Professor Josaphat mentioned, RadarSat 2. This is polarimetric radar. TerraSykes Tandem X. Eros 1 is already completed, finished. Now Chinese Girlfriend 3, RISAT, Indian RISAT, and Argentina, Falcon, I guess it's orbiting. Once we obtain scattering matrix, data is acquired. For coherent case, it is just like a snapshot. We average data to extract information from terrain. This is a second order statistics form. Here, in this form, we have 3 by 3 polarization matrices like covariance or coherency, or 4 by 4 real valued matrix, Keno and Miller matrix. This is effective for incoherent case. For averaging, it's very powerful. Anyway, starting from here, we can create any polarization matrices. But how many independent polarimetric information is there? Usually, we assume SVH is equal to SHV. This is This applies for monostatic radar. Monostatic radar means transmitter and receiver is in the same location. Normal radar satisfies this condition. In that case, HV and VH are same. In this condition, how many independent parameters? For coherent case, relative scattering matrix is absolute value HH here, 1, 2, 3, 3 amplitude and 2 phases. In total, 5 parameters are here in relative scattering matrix. For in coherent case, such as covariance or coherency matrix, total number becomes 1, 2, 3. Real part, imaginary part, real, imaginary, real, imaginary. In total, we have 9 parameters here. So number 9 is much more than those of dual or single polarization data. We have to utilize it. We take advantage of this number. If we look at coherency matrix, it looks like this, the same one. T11 is corresponding to surface scattering mainly, not exactly, but close to surface scattering. T22, double bond scattering, and T33, volume scattering. These are related, closely related to physical scattering mechanisms. If we add these 3 terms, it becomes total power, radar power. Just like a addition of previous scattering matrix. The same. So using this covariance or coherency matrix with 9 parameters inside, we make HV basis analysis. For example, we assign color code HH as red, HV as green, VV as blue, and make a color composite. In a similar way, in Pauli basis, we can do it. There are another way, mathematical way to deal with these matrices with eigenvalue analysis and scattering power decomposition method. Let's take an example. It's easier to understand by images. Color-coded image shown here. This is HH, HV, VV, normal covariance matrix type imaging. This is coherency matrix type imaging. Right-hand side is scattering power decomposition type images. So just comparing 3 images. Which one would you like? I like this one. So I would like to explain scattering power decomposition, which we have been engaged in for many years. This scattering power decomposition is based on the experimental evidences of measurement. The concept is just like this. Measure scattering matrix, coherency matrix is here. By scattering matrix, we can create this coherency matrix. From here, we decompose 4 powers like this using scattering model, surface scattering, double band scattering, volume scattering, and helix scattering. How can we do that? This is experimental evidence. If we look closely, the surface scattering, it is like this. Suppose this is a bare soil surface, like crop field or rice paddy field. Scattering matrix becomes like this. Each polarized wave impinges and returns back. The direction is opposite. So it is minus A. Reflection coefficient is minus A. V polarized wave also return opposite direction, so minus B. Cross polarized component is almost zero. So in relative form, A00B, HH and VV are in phase. For black scattering, B is larger than A. This is experimental evidence. This is one evidence. And the next one is right angle structure. When each polarized wave impinges on the surface, then the direction becomes opposite. And once again, this wave hit this wall and returns back. The direction once again with reversed. So the direction is the same. So we have A here. But V polarization goes like this and goes like this and goes like this. The direction is opposite. Well, it becomes minus B. If we check the sign, it is 180-degree difference, out of phase. For dielectric material, it is not 180 degrees, usually 130, 140 degrees. In mathematical form, this scattering mechanism can be written like this. Real part HH-HB complex conjugate is positive and negative. The third evidence is called reflection symmetry. This applies for natural distributed objects such as forest or trees, crop fields, bushes. Here's a photo. Suppose how many, imagine how many scattering points here, numerous points. If we sum up this complex number, the limit becomes zero. This applies for the data sets. Taking account of these characteristics, we make up model expansion coherency matrix like this, using unknown parameter beta and alpha, and for dipole combination here. Anyway, we prepare this modeling and expand, measure the coherency matrix into 4 parts, divided into 4 parts, where P corresponds power. T is something previous modeling. So total field, total power can be obtained by diagonal component. And in this expansion, we only have 4 terms. T11, 11, 11, 11 is counted here. T22 is counted here. T33 is counted here. T23 is accounted for here. T12 here and here. So in total, 6 parameters out of 9 are accounted for this expansion. Helix term, this term is added for accounting for this non-reflection symmetry. Anyway, we just expand measured value into 4 terms. Just comparing this term, T23, other terms are 0, we can immediately obtain pH power. Just comparing here and here. It's easy. From T23, we can obtain power, volume scattering power PV. It's directly obtained. The remaining is 3 equations from T11, T22 to T13. 3 equations and 4 unknowns. 3 equations and 4 unknowns can be solved by approximation, just reducing 1 parameter. This is accomplished by considering physical scattering phenomena. If we eliminate one of these, it's possible to derive PS and PD, these power directly. It's very simple. So this is the composition algorithm. It's very simple. It looks like a small character, but it's simple. Just taking average. From average, we retrieve 2 powers, and the remaining 2 powers can be obtained in this blue and red rectangle. We have 4 powers. Once we obtain scattering powers, 4 powers in an imaging window, n by n pixel, 5 by 5 or 7 by 7, in any kind of pixels, we assign blue color for PS, red color for PD, green color for PV, and compose it. From here, now, we can see electromagnetic wave here. From here, it's possible to specify scattering mechanism. Green area is tall vegetation, trees, or something. Red comes from double bond structure, urban area, as well as tall trees. And blue comes from bare soil surface. Using this technique, we have been improving the decomposition algorithm. Pioneering work is Doden and Freeman, 1998. Right now, 6 components scattering power decomposition. I do not go into the detail, but if you are interested in other decompositions, for these decompositions, please see this book, relatively brand new book, written by myself last year, Polarimetrics Imaging, Theory to Applications. This details everything about it. Okay, then I would like to show some examples of the composition image using ALOS1, ALOS2, and PolSAR, airborne SAR X and L. Since we have PS, PV, PD, a lot of scattering powers, their powers are listed here. For PS, surface scattering power, this power is effective for disaster monitoring. volcano activity monitoring, glacier movement, or landslide, flooding, snow accumulation. There are various kinds of applications. Let's see. Yeah. Today, just 10 years ago, great earthquake hit Tohoku, Japan, East Japan. And the great tsunami came to this Ishinomaki city. And this is a decomposition image before the earthquake, tsunami. And 1 month later, approximately 1 month later, Eros took the same area with polarimetric mode. Just comparison of the composition image, you can immediately find the difference. Pink colored area is man-made object, residential area and buildings. But here, here, and here, you can see blue color, light blue color. This means surface scattering. These areas are actually wiped out by tsunami. And the survey showed these corresponding area, totally wiped out. Sea is also affected. Aquaculture destroyed. Surface scattering, PS here, this blue comes from volcano ashes after the eruption. Eruption occurred here, Shinmoidake volcano, and volcano ash spread like this. I think Indonesia has a lot of active volcanoes. It may be effective. In order to enhance the landslide area, I temporarily changed color coding like this, PD from red to blue, PS from blue to red, just changed 2 colors, and like this. And PolSAR L2, L-band SAR, took over Totsukawamura in Japan after huge, big typhoon and heavy rainfall. These are mountains, but you can see red spots like this, here, here, here. After this landslide, we checked the area by Google Earth. This corresponds to here, this one to here, this one to here, this one to here. All red area is right, accurately detected. Another one is Kumamoto earthquake in Kyushu Island in Japan. This is before the earthquake. The image was taken by airborne PolSAR, X-band. The resolution is 30 centimeters before the earthquake and after the earthquake. Just compare. Now you can immediately find the change. Here, here, and here. This looked like photo. And by taking the advantage of high resolution mode, we expand this area, landslide area, in 100% resolution, 30 centimeter resolution, PolSAR 2X. Minami Aso village. This was taken 2016, April 17th, just after the earthquake. The bridge collapsed. And 1 week ago, I heard the news, new bridge was built, completed, after 5 years. Road is covered by mud. It looks like real. Just changing the color coding, PS, PD, we can see this image. This is a river. It's amazing. I think this image is much more than optical one. This image was taken approximately 10 kilometers above upper sky. Okay, then I will go to the example of double bound scattering power, PD. This is effective for urban area monitoring, something like this. Here, you can see green area. This is a forest, boreal forest in Canada, northern Canada. The location is depicted here. In the center, you can see red area. This is Fort McMurray city. This is surface scattering area. But unfortunately, there was a big fire, forest fire. The color changed to orange, like this. Burnt area exhibits orange color. This is because this one. In normal situation, volume scattering PV is dominant in forest area. But if fire occurs, branches, leaves and branches are fallen off, burnt and fallen off, leaving the stem alone. When wave impinges, then it reflects and goes back. Double bounce effect occurs. Double bounce is red. Red plus green produces yellow or orange. So forest fire can be detected. Similar phenomena, not a fire, but rice growth, rice growing stage in paddy field can be observed in Niigata, Japan. Niigata is very famous for rice. This is March. Main paddy field is bare soil. Surface scattering dominant, so it's blue. In June, after plantation, the rice stems becomes approximately 10 centimeter or something. It is transparent for L-band wave. So the paddy field is just like a water surface. Water surface does not reflect any echoes, or it looks black. But in August, tree stems grows up approximately 50 centimeters high. If the planting law is orthogonal to radar illumination, it causes double bounce. Double bounce means red. So we see increasing red here. Okay. Another interesting is flooding. This is Amazon. Amazon River is very famous for flooding. Upper image looks like normal, all green, but lower one have yellow zones like this, where something here. The length from left to right is 70 kilometers. From here to here, 40 kilometers. It's very big area. The reason is maybe flooding. Before flooding, in normal situation, the dominant scattering is volume scattering, PV. Surface scattering is small. Urban frequency can penetrate these trees. For flooding case, inundated area expands beneath it forest. The frequency penetrated through trees go to the surface and returns back like this. The reflection coefficient here is much more bigger than in this case. We have strong PD, and the PD red, PV green makes yellow color. That causes this difference. It's immediately fine. This one, and how about this big area? This looks like something like art, river flow, oil. It looks like oil painting. Small branch river here. It's amazing. Then I will go to volume scattering power, PV. I will show some examples observed by Claude Paul mode of AROS 1, AROS PulSAR 1, and AROS 2 PulSAR 2 polarimetric data. You know, this is Mount Merapi, a volcano Merapi, very famous in this country and also famous in Japan. It collapsed, I heard, almost 10 years ago. This is same image, same data, but 6ST, 6-component scattering power decomposition, and 4-component, general 4-component decomposition. This is optical image. I heard the direction is in this way, north is in this direction. Our mentor, Professor Emeritus Borner, visited Indonesia, invited by Lapang. The photo was taken at that time. You can see mountain here. I heard volcano ashes is very severe in this side, and the pyroclastic flow is very big in this side. Blue means surface scattering. Another data here, it looks like beautiful, but very, what to say, blue surface scattering. This is new volcano here. This is located close Java Island, east corner of Java Island. Lombok in Indonesia. Oh, very vivid image. Crater can be seen clearly. And this red color comes from, I guess, tall vegetation, something like tall rice stem, I guess. This is Gannan Agung volcano, Bali Island. You can see lava flow trace of lava flow. Here, pink color is a man-made object, residential houses. This pure red comes from vegetation. When looking inside crater, we can see some pink color here and here. What is it? I checked Google Earth and I found, oh, residential area inside. Inside the crater, we can see residential houses. Oh, it's surprising. This is another example. Bandung. Sorry, not Bandung. Ambon. Sorry. Natural dam collapsed. Here you can see natural dam, but this dam was collapsed and downward flown away and caused a tremendous damage. Natural dam collapse in 2011, July 25th. Village was suffered from the flooding. This area, the Google Earth image is like this. This is an Eros2 image. These two images are deforestation in Malaysia, in Kalimantan Island. You can see artificial blue color here. This is 2007 and 11. New one came here. This is forest cut. If forest trees are cut, then bare soil appears. Bare soil reflects surface scattering power, so it becomes blue. After several years, regrowth occurs and plantation trees, palm oil tree grow up. And a little bit double bounce occurs. So first it was blue, but the blue color faded away because of mixture of various components. This is brand new. So it's possible to see the deforestation, just decomposition of polarimetric data. There are several places in Kalimantan this and this same area. The difference is just the acquisition time, 2015, April 9. Sorry. August 28th. Red case, trees, vegetations are grown up. Double bounce occurs. In addition to the scattering mechanism change, we can still see blue area expanded a little bit. It's possible to see changes by scattering mechanism changes by color. Just looking color, it's possible to find out what's happening there. A lot of plantations are there. This dark green shows plantation, and bright green shows natural forest. Almost plantation fields here. This is a forest image, but we can see various colors inside because L-band wave can penetrate into forest and brings back the information inside. We can map the area like this. Optical sensor cannot do this. X-band radar cannot do this because shallow penetration. L-band can go deep inside of the forest. This is east side of Kalimantan, a beautiful image. Forest, mountain forest, bare soil surface scattering is blue, urban area. In addition to urban area, in the sea surface, we can see spots like this. This is ship, double bounce from water surface, and ship body causes double bounce. So we can immediately find ships here. This is Aperture venue, Denpasar in Bali Island, Denpasar city. I hope somewhere here Aperture will be held. And I thought this black line is water, but it was different. This is an airport runway across here. And I checked this red color by Google Earth. So it looks like a paddy field, maybe tall rice stem caused double bounce scattering. I have seen similar patterns in South India and Myanmar. Maybe tall rice, I guess. Very beautiful. Mountains can be seen clearly. Okay, in summary, I presented PolSAR imaging by scattering power decomposition. Scattering power provides color images easy to understand for everybody. Each color has its physical scattering mechanism. So just looking colors, it's possible to guess what's happening there. So if you are interested, please visit our website, wave.ie.niigata.ac.jp. There are, if you find this image, just click AROS1, AROS2, PolSAR, X and L. You will find map, world map here, Southeast Asia, India, or something. You can find various images are there. Okay, one last slide. This is a good news for you. Global AROS PolSAR quadrupole images, more than 250,000 images, scenes, are available now. This website, https GSRT land browser index HTML, polarimetric data, scattering matrix data, level 1.1, and the decomposition images are available from this website, downloadable. Anyone can visit and download. All AROS1 protocol data set and images are there. It's free of charge. And the second one is partial AROS2 PolSAR2 quadrupole images. This is AROS1, this is AROS2, but for AROS2, download is not available. This is just viewing image. Similar AIST government JP's website. Recent images can be seen from this site. Okay, time is coming. I would like to close my talk. Thank you for your attention. Okay.
Thank you very much, Professor Yamaguchi.
Mm-hmm.
Yeah, I think yes, many students, young scientists, yes, who learned today. Yes, I think it's you know,
thank you.
It is a good opportunity for them, yes, to know more about the polarimetric SAR. Yeah.
Okay, thank you.
Okay, as do you have some question? Please mention on the, we prepare the question sheet. Yes, you can read on the chat. Yeah. Okay. Thank you very much, Professor Yamaguchi.
Mm-hmm.
Yes. Yes.
Yeah.
And we want to move to the next presenter. Yeah. The next presenter is Professor Sun Hongbo. Yes. Professor Sun. Okay. Yeah.
Yes.
Okay. Yes. Okay. And the time is for you. So you can start your lecture. Yes, for 1 hour. Yeah. Thank you.
Okay. So just confirm. Can you see my slide?
Okay. Yes. We can see. Yeah. Okay.
That's good. Okay. Good afternoon. Very glad to have an opportunity to give a tutorial for the APSAR 2021 conference. Actually, my talk is not directly related to synthetic Aperture radar, but I think it's still very important for the radar community because I'm going to address the very important currently it's for zoom detection by radar. because we all know that the Zoom had been used more and more widely. So it also became a critical issue for many governments to efficiently monitor the Zoom's operation. So I think this is also a good opportunity for the radar community to produce some product or even do some research on Zoom detection. Okay, this is the content of my presentation. At the beginning, I will give some introduction about the Zoom threat and also the detection challenges. After that, I will introduce the microdoppler signatures of Zoom Tetuko. Then the third part, this is the most important part in my talk. I will highlight how the advanced signal processing can help for the Zoom detection and also the classification in the real world scenario. Okay, here I want to emphasize this because maybe you can read the Zoom classification detection in a lot of papers. I would like to say maybe most of the paper actually the result or the data they measured are not really in the real world scenario. So in my presentation, maybe you can show some examples of the Zoom detection using the real operational radar system in the real world scenario. Yeah, then finally I will give a summary and a perspective. Okay, let's go to the first part. Okay. Okay, I think now everybody knows the Zoom has been widely used for many applications. For example, maybe even some of you even have your personal Zooms to take photos or videos. And the Zooms also be used for the agricultural automation. For example, for spray the pesticide, also for field survey of the farmland. It also be used by the infrastructure inspection of the infrastructures. Also maybe the smart farm, checking the cows. Also the Zoom can be used for the disaster assessment. Yeah, of course, it's used by the police and security force to monitor the suspicious persons or in the vehicles. Okay, in this slide, I show a very important application for the Zoom, particularly in Southeast Asia countries for the oil palm plantation. Because we know that oil palm is maybe one of the important resource for the Southeast Asia countries, maybe also including Indonesia. They have a large area of the land for oil palm plantation. So normally, okay, it's a very labor-intensive work to monitor the oil palm plantation because the area is so large. Okay, so it's very labor-intensive. But with the help of Zoom, some work can be much easier. For example, it can install, for example, a camera or the infrared sensor on the Zooms. Then based on the image obtained by the Zoom, automatically count the number of trees, number of oil palm trees. Then based on the image, we can also monitor how the oil palm trees grows. And we can even use the hyperspectral image to evaluate whether the palm tree was affected by some disease caused by the pest. Okay, I think you can find some very interesting results in this report. For some other application, yes, in Singapore, the Singapore Post has ever did some trials to validate the using of Zoom for parcel delivery. They try to deliver the parcel from the shore to the ship or to the small island. So this is much more efficient than the conventional way, because in the conventional way, you need to hire a small boat, send the postman there. Okay, so now with the Zoom, it can be much. Another trial in Singapore about 1.5 years ago, it's the air taxi. Yeah, the company had ever showcased in the Marina Bay area of Singapore. So, okay, maybe after a few years, maybe it can be a popular transportation mode for the air taxi. Okay, there are many applications, but concurrently, there's still a lot of misuse of drones. For example, the drone may be misused for illegal picking, for drug smuggling. It also may be used by the terrorists to carry a bomb because if the drone collides with the person, or if it obstructs the flight route of the airlines, then the drone may also invade some sensitive areas. So that's why, okay, so it's very important to monitor the drone. Okay, in this report, you find some measurement was conducted by the Virginia Tech. They investigate how serious if the drone impact hit the people. So you see, actually, it will be very dangerous if the hit the people, particularly for the head. It will cause very serious injury. Another university is in the United States and also conduct some experiment to see when the planes and drones collide. Okay, because previously, okay, we can imagine, we think, okay, normally the drones are very small. So it may not be a big issue if it collide with a very big aircraft. But in this experiment, you can see, you see some pictures here. So when even a very small drone, it's just a DJI Phantom 2, just 1 kg, if it collide with the wing of the small aircraft, you see the drone did not shatter on impact, but it opened the leading edge of the wings and bore into the structure, totally damaged the main spar in the wing. So this is very dangerous for the aircraft. Okay. Actually, I also want to highlight in this experiment, they just use a very small drone, just 1 kg drone. They also use a very small aircraft like this. Okay. This small aircraft, the flying speed is relatively quite low, just 380 kilometers per hour. So we all know that for the normal airliner, the flying speed is much faster. So you can imagine if the drone collide with the airliner, the impact will be much more serious. So that's why I think maybe you can remember about 2.5 years ago, some illegal flying of drones were observed in the 2 airports in London. So the 2 airports had to be closed, and maybe tens of thousands of passengers have been affected. This is very serious aviation public safety. Okay, now, okay, for drone monitoring equipment, we always have some desired functions. Okay, first of all, yes, we want to detect the drones. This is the first function we must have, but just detection is not enough. So we also want to do the classification or identification. So that means we want to separate the drones from other type of detected objects, for example, the bird. Okay, we also hope to identify the particular model of drones. Then after the classification and identification, I also want to localize the drone and track the drone. Okay, track the exact position, and also so that we can predict the trajectories. Then finally, based on all the information we obtain, then we need to do a evaluation on the threat level of drones. Then also maybe alert for some further actions. Okay, in this table, I summarize different types of the drone monitoring and the drone countermeasures. Okay, for the drone monitoring, the different types of sensors. First of all, we can use the radar sensor. Yes, of course. Somebody also used the EOIR sensor, for example, the camera. The acoustic sensor can also be used for drone detection. Then the last one is the RF analyzer. The RF analyzer is also widely used to sense the radio signals from the zoom between the zooms and the remote controllers. Okay. And for the zoom countermeasure, the RF jamming has been widely used. Some Euro countries or even the America also use the net gun to physically shoot down the zoom. I know in the United Kingdom, they had ever conducted some trial to train some birds, for example, the eagle, to physically to catch the zoom. And also for the military application, it's much more popular to use high power laser or microwave to take down the zoom. Okay, but here I want to highlight: no equipment perform all the desired functionality at the same time. For detection, classification, localization tracking. So okay, no sensor can perform all. Okay. Here I gave an example. Okay, this is a good example of the integrated counter drone system. It's developed by a Europe company. Yes. Okay, we can see in the one platform they even integrate the optical sensor, also the radar sensor, acoustic sensor. They also integrate the RF analyzer and also the RF jammer. Okay, so that they can not only just sense monitor the zooms, they can also use the RF jammer to take down zoom. Okay, so this is a very good example of the integrated sensor system. Okay, now we focus on the zoom monitoring sensors. Okay, I summarize the pros and cons for the different type of sensors. First of all, the RF analyzer. The advantage is it has very low cost. And also, it's possible to detect multiple zooms and controllers. But unfortunately, because this RF analyzer, they only detect the radio signal between the zooms and the remote controllers. So if the zoom just fly in an autonomous way, the RF analyzer cannot detect the zoom. Okay. And also the RF analyzer is difficult for it to localize and track the zoom, and it's also less effective in a crowded RF spectrum. Okay, the next, the acoustic sensor. Acoustic sensor means a microphone. Okay, to just hear the sound generated by the zoom, the motors. It's very low cost, yes. But unfortunately, the acoustic sensor usually have very limited detection range, maybe just 100 or 200 meters. It's also very difficult to discriminate the zoom signal from the background noise. Okay, particularly in the urban area, it's a lot of reverberations and echoes. The performance of the acoustic sensor will also be degraded. It also has very poor localization capability. Okay, next one, the EOIR sensor. Okay, the EOIR sensor has been widely used for the zoom because it can provide the visuals for the zooms and also its payload. So means the controller you can just directly visually see the zoom, how the zoom look like. So it has a very good classification and identification capability once it's detected. But one of the main drawbacks of the EOIR sensor is it has a very limited field of view. It cannot do the surveillance for a wide area. Okay, and it's also very difficult to discriminate the zoom from the background. Also, sometimes it has a very high force boundary. Okay, and also in a very bad weather conditions, and also at night, normally the EOIR sensor cannot be used. Okay. Okay, last one, radar sensor. Yeah, radar sensor actually can a lot of advantage compared to other sensors because it can achieve very long range detection. It can easily do surveillance over very wide angles, and it can easily track and localize the zooms. Okay, it can also handle multiple targets simultaneously, and also the radar sensor can operate in all day and all weather conditions. Okay, it's much less weather dependent. But the very challenging task for the radar sensor is the classification and identification. Okay, and also for the active radar sensor, normally we also need some RF spectrum occupation. Okay, but for the conventional radar system, I want to say it may not be easy to detect the zoom because, okay, I summarize the reason in this table. Okay, very direct. Okay, for the conventional radar system, okay, normally it can only detect either a big target, for example, the big aircraft, airliner, fighter, or some very fast target, for example, the missiles or even the artillery shell. Okay, so this is what the normal radar detects, either a very big target or the fast target. For the zoom, particularly for the consumer grade zoom, we know it's flying very slow and it's also very small. So the echo signal zooms normally will be mixed with the echoes from the bird, or the bat, even some insect. Okay, because all the targets are small and slow flying. Okay, so normally the zooms will be below the conventional detection threshold of the radar system. Okay, and as I just mentioned, even the radars can detect the zoom, but it's not easy to separate the zooms from echoes from other targets. Okay, you see, as I just mentioned, the zoom echo signal may be mixed with the bird, the ground vehicle, even the bicycle, even the trees. Because when the wind blows, the tree leaves may shake. So all these signals, all these will generate the Doppler signal. All these signals will be mixed together. Okay, so sometimes for zoom detection, the radar performance is not limited by the hardware, but the software. So that means the radar software must be capable of separating the zoom echoes from all these other classes. Okay. Okay, next. How can we separate the zoom signals from other echo signals from the birds or even the vehicles? Okay. Yes, the answer is the microdoppler signatures. We need to separate the zoom signal from all these some other moving object. I think it's also very common for the radar. The walking person, the bicycles, cars, the birds. Or even, oh yeah, this is very important for the aircon, because the aircon, the fan also rotates. Actually, this the echo signal of radar, this is very similar to the rotating blade of zooms. Okay, so this is also very critical. You need to separate the zoom echo signal with the echoes from the aircons. Okay, because this is very common in the urban area. Yeah, okay. This slide summarizes the theory of the blade echo signal of zooms, because this is for all zooms they always have a rotating blade. Okay, this slide just derived the mathematical model of the echo signal from the blade. I think maybe I don't go through the mathematical details here. Maybe I just go to this slide. I think it's easier to understand. Yeah, this is a very simplified model of the blade. You see, okay, when the blade is perpendicular to the radar lamp side, okay, at this position, you will receive a very strong signal from the blade. Okay, so when the blade rotates, the signal will be weaker. So after one whole run, or after half run, then the blade go back to this position. We receive another strong echoes. Okay, so in time domain, the echo signal from blade will look like this. Okay, we will receive some very strong signals periodically. Okay. Then based on this time domain signal, actually the interval between the two peaks of the signals, then we know we can derive the rotation speed of the blade. Okay. Then based on the time width of this signal, this is proportional to the length of the blade. Okay. So that means based on this time domain signal, we can derive a lot of useful information for the zoom. For example, the length of the blade, even the rotation speed. Okay, this is the time domain signal. If we convert this time domain signal into the frequency domain, we also get periodic peaks in frequency domain. Also, based on the intervals between the two peaks, we can also derive the similar information. For example, the length of the blade or even the rotation speed. Okay. Okay. Next, in this slide, I show the simulation results for the blade echo signal. For example, okay, the top left corner, this figure shows the blade, even number blade, which is, for example, if there are two blades, okay, that'll be like this. Okay, this is the spectrogram. So that means it's the horizontal axis is time, the vertical axis is the Doppler, the microdoppler. Okay, so for even number of blades, the spectrogram will be like this. Okay, if it's odd number, for example, n equal to 3, the spectrogram will be like this. Okay, then from this spectrogram, from these microdoppler signatures, we just analyze this. We can derive a lot of useful information. We can know the number of blades is even number or odd number. We know we can derive the length of the blade. We can even derive the number of blades. We also derive the rotation speed of the blade. Okay, then based on this, so we can know a lot of information about the tune. Okay, this slide I show some examples, the simulation results of the different type of tunes. For example, the fixed wind tune. Usually, the fixed wind tune has a very small blade. The rotation speed will be much faster than the rotary wind tunes. Okay, this is a fixed wind tune. Then this is the helicopter tunes, just two blades like this. Then quadcopter, it has been widely used. And there are also some hexacopter, even octocopter. Okay. So we can see from all these the microdoppler signature. So based on all these microdoppler signatures, it looks we can easily classify the different type of tune. Okay, it looks very easy. But here, okay, I want to highlight all these signatures. Okay, all these signatures was obtained with very short integration time. That means because we need to have very high time resolution to get this microdoppler signature. So I believe maybe you can find the similar microdoppler signature in maybe in a lot of papers, all like this. Okay, so all these I just want to highlight. They were obtained with a very short integration time. For example, with just 0.6 milliseconds in the simulation. Okay, but normally in the radar detection, long integration time is always desired because with long integration time, make sure we can have higher processing gain. So if the integration time is very long, for example, 82 milliseconds, what we have is like this. With long integration time, we will have very poor time resolution, but we will have very fine Doppler resolution. So if we see the detailed Doppler spectrum, so we can see this structure. So based on this, based on the interval, for example, based on the peaks between the interval between the peaks, we can also derive a lot of useful information, as I just mentioned, the rotation speed, the length of the blade, right? Okay. Okay. But here, I want to highlight all these are just based on simulation. In the real world scenario, it's not like this. Okay, next. Okay, we go to the real world scenario. Okay, for example, I give a typical point-based radar system. We also use this radar system to detect the drones. Okay, this is divided by the colors. It's a man-portable surveillance radar. I think it has been widely used in the Southeast countries, Southeast Asian countries. Okay, yeah. Okay, we know in the real world, the radar system will always need to cover either 360-degree or a very wide area. So that means the radar beams must be always in scanning. Okay, so normally we hope to have a very rapid update rate. Rapid update rate means the beam must be scanned very quickly. Okay, but the fast beam scanning means for a particular target, we will have very short dwell time. Short dwell time means less integration time. Less integration time means we will have very poor Doppler resolution. But of course, poor Doppler resolution means a degraded performance. Okay, now we find that there is a contradiction. We cannot solve it. Okay. Okay, as I just mentioned, if the radar can have a continuous illumination to the target, to the dunes, we can have either the spectrogram microdoppler signature like this with a short integration time, or if we take a long integration time, it'll be like this. Okay, so all these have a very fine microdoppler signature. Okay, but unfortunately, this result can only be obtained if you have a continuous illumination to the target. But as I just mentioned, in the real time, the radar beam will always need to scan in quickly. Okay, you won't have the radar beam won't point to one target continuously. Okay, so for this case, we have intermittent illumination due to the beam scanning. So that means we will have very short integration time. Okay, then for the real radar system, we always detect the dunes, detect the target in range and Doppler. Well, okay, this result is a very typical measurement result for the real radar system. As I mentioned just now, it's the Thales portable ground-based radar system. Okay, so for this system, you see we cannot see clearly the microdoppler signatures of the dune. Okay, so this is the real world scenario. Okay, since now to get the Doppler or the microdoppler signatures, okay, normally we use the Fourier transform. Yeah, this is the conventional way. But I think now everybody knows the Fourier transform has a very poor resolution. Maybe some of you know there are some high resolution algorithms, for example, the minimum variant distortionless response (MVDR) and also the MUDIC. These are two typical high resolution algorithms. I think they have been widely used. For example, the direction of arrival estimation. But here I want to highlight all these high resolution algorithm. They need many snapshots or the secondary data to estimate coherence metrics. So, but unfortunately, in the Doppler or microdoppler estimation for the dune target, we just have one snapshot of data. So that means we cannot estimate the coherence metrics. We cannot use the typical high resolution algorithm. Increase the Doppler resolution. Okay, now, actually, in 2010, there's a quite new algorithm. It's called IAA. It's an iterative adaptive algorithm. It's a data-dependent iterative adaptive algorithm. One of the most important advantages for this algorithm is it can work with even one snapshot. Okay, it don't need to estimate coherence metrics. It can estimate the high resolution spectrum with just one snapshot. Okay, I highlight this is the most important advantage. Maybe I don't go through the mathematical details for this algorithm. Show some the simulation result. Okay, for the top left, this is the simulation result for the ideal case, no noise. Now I simulate two Doppler signal. For example, okay, this is the conventional FFT spectrum. Then with this IAA algorithm, we have the two ideal Dirac function, the impulse. This is the ideal case, no noise. Then the two figure in at the bottom. The left one is the high SNR, 20 dB SNR. The right hand side is the low SNR, -5 dB SNR. So you see for both cases, the IAA always give a much higher resolution with just one snapshot at highlight. Okay, it's achieved much higher resolution than the FFT. Okay, and also I also compare the root mean square errors of the for the Doppler attenuation of IAA and FFT. So you see they have almost the same accuracy. Okay. So we try to use the real data. Yeah, okay. This is the experiment we conducted in Singapore. We use the Thales radar, as I just mentioned, to do the June detection. Okay. Okay, this radar, I forgot. This radar is in the X band, about 10 gigahertz. It's with the FMCW form. Okay, normally this is the surveillance radar, so means during the operation, the radar beam is always in scanning. So the effective dwell time for June targets normally is less than 14 milliseconds. Okay, very short. Okay, this is the map. Okay, this is the yellow dot indicates the detection, the detected June, the trajectory. About 1 kilometer. Okay, you see the video for the experiment. Okay, you see the radar antenna scan over a very wide area. Here you see this is a fixed beam June we fly. Okay, in our experiment, we use actually we collect a lot of data for different type of Junes. You see even the rotary wing and also helicopter, also even some fixed wing Junes. Okay, this is the example result for a quadcopter. Okay, so we see the figure in the left-hand side is the FFT. So the Doppler was estimated by the FFT, the range and the Doppler plot. Okay, here, this is this big yellow dot is the June body. Okay, the June fly very slow. Okay, all this you see the spread, the micro Doppler spread all Doppler axis. Okay, but due to the low resolution, the poor resolution of FFT, we cannot see the micro Doppler signatures very clearly. Okay. Then we process the same data using the new IAA algorithm. Now you see we can see the Doppler resolution was improved significantly, and now we can see the micro Doppler signature in the periodic peaks very clear. Okay. Yeah, here okay we detect in this data we detect not only this June, this quadcopter June, we also detect a bird because when we conduct the measurement, we can visually see the bird. Okay, here. Okay, this is the result for the rotary wing Junes. Okay, next, this is the result for the fixed wing June. Okay, this fixed wing June, there is a blade here. We know that the fixed wing June, we know the blade rotates much faster than the rotary wing Junes. So in the frequency domain, in Doppler domain, the micro Doppler peaks will be more sparse. In this FFT result, okay, we see because this is fixed wing June, the flying speed is much faster than the rotary wing June. So here the June body, and also here, okay, in this FFT result, we can already see the micro Doppler are very sparse. Also in this IAA result, yeah, it's much more clearer with much higher resolution. Okay, okay, this is because the rotation speed of fixed wing June is much faster than the rotary wing June. Okay, so we compare these two results. So from this the micro Doppler signatures, we can easily classify which one is a fixed wing June, which one is a rotary wing June. Okay, right? Okay, this the first table I also summarize the signal to noise ratio we detected for the Junes and also the bird. For all case, okay, I can say the IAA always achieve better result because normally when we use the FFT to perform the Doppler processing, normally we have to add some a window function to suppress the side lobe. Okay. For example, in our processing, normally we use the Henning window. But this Henning window will be maybe a few dB processing loss for the signal to noise ratio. But when we use the IAA, we don't need to apply this taper function. So we compare all the SMRs for all the Junes and also the bird. We see a few dB higher SMR. So that means we can have an even better detection performance. Okay. The second table summarizes the classification result. Okay, so we collect a lot of data, including the Junes, rotary Junes, fixed wing Junes, and also some non-June target. For example, the bicycles or walking person, or even some ground vehicles. Okay. Then we put all the data, we do the classification. You can see we get quite high correct classification rate for the non-June, fixed wing June, and rotary wing June. Okay. So I think if you are interested, you can find more detailed information about all these trial results from these two papers. Okay, now we can do the summary. Okay, as I mentioned, okay, the first, radar is the most efficient sensor for drone detection. Okay, as I mentioned, the radar sensor can easily achieve a very long-range detection. It can also easily cover a very wide area. Okay, no other sensor can easily do this job. Okay, for example, even if you have a very camera sensor, the camera can easily see the drone, but it cannot do the surveillance over a wide area. Okay. Second, the drone detection and also the classification performance depends not only the radar hardware but also the software. Okay, as I just showed, the advanced signal processing, for example, the higher resolution can greatly help with the classification of drones, just based on the microdoppler signature. Okay. Then the operating environment determines the appropriate solution. Okay, because when we want to detect the drone, the environment may be different. It may be an open area or it may be in an urban area. Okay, for different environment, we should take the different solution. So one size, one radar cannot fit all. Okay, so we need to consider in the environment, we really do we need to achieve very long-range detection or just short-range detection will be enough. We should also consider we should use a standalone single sensor or maybe many distributed sensor. Okay, for some application, maybe the many distributed sensor will be more cost-effective. We may also consider whether we use a centralized control or maybe a distributed control. Okay, here I show some example. Okay, first, what kind of radar is more suitable for the drone detection? Okay, should we use a very advanced radar system to detect a very small consumer-grade drone? Obviously, the answer is no. This just like you use a cannon to shoot a mosquito. Okay, so yes, maybe even a small radar like the radar I just used, this will be more suitable for the drone detection. Okay, here I show some state-of-the-art radar system, the commercial radar system for drone detection. The first one, the square radar, just now we used for the our experiment. Okay, this is the main point. Radar, and Talos had another product for the long-range drone detection. Okay, this radar is different from this. In this one, as you see in the video, the radars cannot need to mechanically scan to cover a wide area. But in this radar system, they use MIMO array technologies, so the antenna, the radar beam can cover a wide area. The radar beam can scan electronically, not mechanically. Okay. We also have another type of radar which is developed in China. You see, it looks like a cylinder, can cover all 360 degrees. They also integrate a camera sensor on top of the radar. So normally they use the radar to do the wide area surveillance, to just scan, to find the target first. Then after the target is detected by the radar, then they can use the camera sensor to just point to the target direction to see whether it's really a drone or whether it's very dangerous. Okay. So you can see in the picture, they install the radar on top of the vehicles and the whole integrated system. Okay, now if we want to detect the drone in urban environment, for example, like this, okay, what kind of radar system is the most suitable? Okay, I think in this environment, you see the drone can easily fly in between the high-rise buildings in the CBD area. But for this case, for this environment, obviously, I think we should not use some big and long-range type radar system. For example, even this one, or even this one, I don't think very suitable. Because even this radar system can detect the drones at very long distance, for example, even 2 kilometers, for example, 2 or 3 kilometers. But this environment, if the drone fly in between the buildings, the radar actually is not useful. It totally waste of the money and the resources to use the very expensive long-range radar system to detect the drone. Okay, so for this, maybe a more effective solution is the distributed radar sensor. Okay, this idea also proposed by our partner Carlos. In this idea, okay, normally if we install the long-range radar system on top of building, it can cover maybe the whole sky above the height of the building. But if the drone, a small drone, fly in between the buildings, we need to use a lot of small, very cheap distributed radar sensor to cover all these gaps between the building. Okay, so for this case, you see, we need to install a lot of distributed sensor. Each sensor just need to cover maybe the distance, maybe just maybe 100 or 200 meters, very good enough. Okay, so for each sensor, it can be very cheap. Okay, so this in total, this will be a much cost-effective solution to cover the urban area, for example, in the CBD. Okay, actually, in the market, there have already been some very small and very cheap radar sensors. For example, I just showed an example. This is from RFB. This is the company from Switzerland. This is a very small module. You can see even with this small module, you can easily achieve, maybe you can detect the drone even at a few hundred meters. Okay. Here you have another example. This is a company from the United States. It's not a module like this. I think this is already the whole system, the commercial product for the radar sensor. You see, you can even install it in the example, small tripod, even the length. Okay, this even for this small radar system, it can easily detect the drones. For example, this Phantom 4 is also a very small drone in 900 meters, okay, very long range. So it will be good enough to cover the gap between the buildings. Yeah. Okay. The way ahead. Okay. What we can do in the future for the drone detection and the classification? Okay. Actually, the techniques I just introduced are all based on the microdoppler signatures. Okay, but sometimes maybe in some very long range, the microdoppler signature may not be observable or may not be detectable. Okay, so for this case, how can we do the June classification without microdoppler? Maybe we can consider to do the June classification based on the velocity, because given the acceleration, because I think the behavior of the flying of the Junes for the velocity and the acceleration will be much different from the bird. Okay, so maybe based on the velocity and the acceleration behavior, we can separate the June's signal from the bird, and also maybe according to the trajectory history of the Junes. Okay? So maybe we can use this information. Okay, sometimes we also hope to have much more accurate classification. Okay, so sometimes, okay, it's maybe not good enough for us to know whether this is the June or this is the rotary June, for example. We also hope to know what the June's payload, okay, what is the June carried? Okay, is it carrying bomb? Okay, so if we can know this, it can provide us much more useful information to evaluate whether this is a threat or whether we need to alert for some other action to shoot it down. Okay, so how to do the more accurate classification of Junes? Okay, maybe we can consider some technology, for example, the coarse-range profiling. Okay, this concept is something like the inverse synthetic aperture radar. But yes, of course, for the June, normally it's very small. It's not easy to form a very nice image of the Junes with a normal microwave radar, because it's limited by the signal bandwidth. But maybe we can have a higher coarse range resolution using the ISA technology. Then with this coarse range profiling, maybe we can roughly know the size of the June. Okay. Then maybe we can also try to use the radar sensor at higher frequency, for example, with a millimeter wave, or even the LiDAR, to get the very fine ISA image of the June. Then with this very high resolution image of Junes, maybe we can know what the June is carrying. Okay, it's a camera of the bomb. Okay, this is just some idea. Maybe I think we should think about, is there any other signatures or any other techniques we can use for more accurate classification of the June. Okay, so yeah, this is the acknowledgement. So I need to thank for the collaboration with our previous partner, with Thales, and also the team in the Nanyang Technological Universities. Most of the work was done when I was there. Yeah, that's all of my presentation. Thank you.
Thank you very much, Professor Sung Hongbo. Yes, this is very nice presentation. Yes. Okay, we have 10 minutes. Yes, maybe we can open some question for you.
Yeah.
Okay. From the floor, if you have some question, you can raise hand. Yeah, and then we will point you later. Okay, and we also prepare the e-certificate. Yes, and the committee already delivered to the participant. Please, you can find the mapping.or.id webinar episode 2021. Please click the link and then fill your name, full name, and then just click, a certificate, and you can get the certificate. We'll open until Indonesian time, yes, 4:10. Yeah, in Japan is 6:10. Yeah. Okay. Who has some question? Okay, if no question, yes.
Prof, I have a question.
Okay, yes, Pendansang.
Yes.
First, about the Professor Josaphat presentation. I really interested to know more about the circular SAR.
Yeah.
And you said that the researcher has the opportunity to get the license or to try to process the data of the CP SAR. And how about the regulation or how to apply to this, to your statement, Prof?
Okay.
That's
Yes.
my first question.
Yes. I think I already answer. Yes. You can find my answer that Chiba University will open the research collaboration opportunity from next April. You can check on the website of Ceres. Yes. Wait a minute. I want to show you. Okay, you get the link? Yes. Ceres.chiba-u.jp. Yeah.
Not yet, Prof.
On the chat. On the chat.
On the
Yeah.
chat.
Yeah.
Wait. Not yet. Maybe the others. Can you get the link?
Oh, yes. I put on the link. Yes. Wait a minute.
Yes.
Yeah.
Oh yeah. Okay.
Yeah. Yeah. Okay. Yeah. You can check this one after beginning of the April. Yes. You can find some information about the collaboration proposal. Yeah.
Okay.
You can propose, and yes, of course, later we made some collaboration and sign some agreement between you and Chiba University. Yeah.
Okay.
To use our CPSAR images. Yeah.
Yes.
Yeah.
Yes, Prof. I also has another question related to the ALOS2 PolSAR, Prof.
Okay. Yeah.
I read some information from some reference that just like the forum in ResearchGate, something like that. Yeah. I got information that ALOS2 PolSAR will be open source data, but I read this this news maybe around 2 months ago, and the news is in 2019, and until now I cannot get the real information about this.
Okay.
Because I think ALOS PolSAR 2 is has the advantage in area like Indonesia, because Indonesia has a lot of vegetation, something like that, compared to the Sentinel-1. Prof, thank you.
Okay. Yes. I think it's the proper person is the JAXA, yeah, to answer your question. Yes, about the as I know that LS2 is not yet open, yeah.
Okay.
But partly of the LS is, I think you can find on the website of the USGS or from the Alaska Fairbanks, some research center. You can use. Also including the Aster and other, images.
Yes.
And JERS1 is you can use. I think it's from the geoportal of the JAXA. It is free of charge. Yeah.
Yes.
From level O. Yes. Or from the raw data. You can use the data. And I also use many. Yes. To analyze the Indonesian area. Yeah.
Yes. Okay. Yeah. Thank you, Prof. Josaphat.
Okay. You're welcome. Yeah. Okay, another question for Yamaguchi Sensei and also Sun Hongbo Sensei. Yeah.
Yes, sir.
Okay, Arifin Zhang, that's all.
Yes, I would like to ask Professor Sun from Singapore.
Oh, yes.
Yes. Yeah. This is relating to the fact that drone is small enough to be detected in terms of perhaps something to do with the parameters of the aperture vis-a-vis the radar itself, and what is the what will be the maximum range? Maximum range can be achieved by the presence, what you call it, receiver, radar receiver at the moment. And I saw that there are some
Okay.
more product being devised and so on. Thank you.
Okay. Okay. So okay. Normally, what I'm talking about is the consumer grade of drone. Okay. So we know the consumer grade of drone is just maybe with a size of maybe from less than half meter, maybe less than half meter, maybe 20 or 30 cm for the like this. Okay, so okay, for to detect this consumer grade drone, okay, normally we what we need is not at a very long distance. Maybe I think, for example, if it's in the urban area, we just need to detect you maybe a few hundred meters will be good enough. Even in the open area, maybe it's in an open area, normally we just need to, based on the user requirement, we just need to detect the drone in maybe, for example, 2 kilometers or 3 kilometers. So actually for the radar system, as I showed, for example, the Thales Square radar, because that radar is the main portable system. Okay, even for some that small radar, it can easily detect the drone. For example, in the DJI Phantom 2 or Phantom 3, it can detect at 2 kilometers. Will be it's very normal. Okay. So even if you use very small modules, for example, as I showed, a very small module like this, even less than the size of the palm, it can detect the drone maybe 200, 300 meters. Will be this is a typical performance for the current radar module or radar system. So I think this, in terms of the hardware, I think it's already good enough to meet the user requirement. So what we need to develop is actually to more work need to be done in the signal processing techniques for the classification. Yeah. Can I answer your questions?
Arvind-san, it is okay?
Yeah. Yes, this is very okay, and thank you very much for your clarification.
Thank you.
Okay, thank you very much. And how about another question? Yeah.
Good afternoon, sir. I would like to ask you, Prof. Josaphat.
Okay, yeah.
Yeah. I have some question actually. The first one is, could you please demonstrate us how to use SAR to one of the area in Indonesia that has already a settlement process, particularly in a vegetation area? That's the first one. And the second one, in your mind, which one is better? We are using synthetic aperture radar or real aperture radar? It's the second one. And the third one is about the minimum pixel of the SAR technology based on the satellite data. Thank you, sir.
Okay. Yes. I will answer based on my knowledge. Yeah. First is the the third one. Yes, it is the resolution. I think is you can find sub meter like the TerraSAR X. Sometimes you can find the sub meter, and yes, normally I think it's after the the law of the remote sensing proof that I think is commonly we can use just more than 1 meter. Yeah, and then the second one. What is the question? Yeah.
The second one is about based on your experience, sir.
Yeah.
We have another technology.
Okay.
Not only synthetic aperture radar, but we have real aperture radar. Which one is better for you?
Okay. I think you must know about the basics. Technology of the synthetic aperture radar. Actually, in the synthetic aperture radar is to derive high resolution. Yeah, it means I think it's based on the application. If you want to apply for the for the mapping or to classify something, I think is the synthetic aperture radar is better. Yeah, and upon the complexity is of the analysis is, of course, yes, synthetic aperture radar is more complex, yes, compared to the real aperture. Like one of the application for the ground penetrating radar, yes, it is commonly used the real aperture, yes, but you can also combine using the synthetic aperture radar. Okay, and then the first question is about the demonstration of the Indonesian. It means it is the application for the what is the biomass monitoring or something.
For example, the settlement process, sir.
Settlement.
Yes, settlement process. It means we need to measure the deformation of the settlement process in Indonesia, particularly in a vegetation area.
Okay. Yes. You can read my paper. I think it's my paper relating the the ground observation. It means the like especially subsidence. Yeah. My paper at TGRS is about the subsidence at the Bandung. Yes, and GRS IEEE GRSL later is about the settlement area of the Jakarta. Yeah, and another one is about the Lapindo, and also I'm doing also the Semarang city. Yeah. Almost all of my observation, I use the L-band, yes, because the L-band can reduce the effect from the vegetation. Yeah, so it is just my recommendation. If you can get the low frequency of the synthetic aperture radar, it is better. Yeah, I think right now it's just L-band is the most lowest frequency. If you can find the P-band, I think it's more better. Yeah, but right now I think yes, L-band. Yes, it means the LOS LOS 2 and JERS 1 is I think the good one. Yeah.
Thank you, sir. It's a pleasure if you could share to us the website or the link of your presentation, or even your
Okay.
Thank you very much, sir.
Sorry, you can send email to me. Yes, I put on the chat is my link, and then I can share my paper later.
Thank you very much, sir.
Okay, you're welcome.
Yeah, really appreciate it.
Okay, maybe another question.
There is a question from Diha Umar Hadir to Yamaguchi Sensei.
Okay.
In the chat box.
Yeah.
Okay. Yes. Pak Deha. Yamaguchi Sensei. It is the question from Diha Umar Hadi. Yes. The question is there any limitation of the polarimetric SAR or PolSAR decomposition compared to backscatter value? Yeah.
Pardon, once again, please.
Okay. Is there any limitation of PolSAR decomposition, compared to the backscattering value? Yeah.
Stay.
Yeah. Maybe it is polarimetric. The polarimetric compare just polarimetric decomposition compared to just the backscattering analysis. Yeah.
Oh, I see. Yeah, backscattering analysis. includes single polarization, dual polarization, and fully polarimetric information. Backscattering, if you say HH only, it is one backscattering. HV, second backscattering. VV, third backscattering. Polarimetric means 3 or 4 combination backscatterings. It is a multiple scattering coefficients. You may have the idea. So if you use polarimetric data, the backscattering becomes 4 times compared to single polarization backscattering. You understand?
Yes, I understand. And thank you very much for the explanation. But what about the limitation of using the
limitation? It's the same as radar performance. If
yes.
You mean limitation means by range or resolution or what?
Yes, I mean the disadvantage of using the decomposition compared the disadvantage, like the limitation for this technique.
No, I think there's no specific limitation disadvantage.
Okay, so it's very good to apply the polarimetric decomposition compared to just relying on the backscatter values. Thank you very much, Professor.
Data just expand the capability of radar sensing technique.
Thank you very much.
Okay, another question. We have 3 minutes, yes, until we, the time to close the e-certificate. Yeah. If you have some question for Professor Sun and also Professor Yamaguchi, please deliver.
Professor Josaphat?
Yeah.
I saw the question, but actually I don't very understand in the chat. To me,
okay. On the chat, yeah. Okay. Oh yes. One of question to Professor Sun. Yeah. It says, can a radar jammer be fitted to a drone to prevent being detected by the radar? What is?
Radar. Sorry, can you repeat? I didn't get the point.
Oh yeah. Oh, wait a minute. Yeah. Maybe I can put on the chat. Yeah.
Okay. Yes.
Yeah. And then the question from Dimpos Pasaribu. Yeah.
Oh, radar jammer be used to prevent being. Okay. Normally, for as one of the counter drone measures, it's RF jamming. The RF jamming means for most of the consumer grade drone, the drone is remote controlled. So normally the person use the remote controller to manually control the flying of the drone. So that means there is the radio communication between the drones and with the remote controller. Okay, so normally if we want to stop the drone, we will transmit a jamming signal to stop the radio communication between the drones and the remote controller, so that the drone don't know where to fly. Okay, so some drones have been programmed. If the signal had been jammed, it will automatically go back to the remote controller. Okay, this is the normal way for the RF jamming stop the operation of Zooms. But the radar jammer, I think is in. I think maybe radar jammer can work, but maybe it's it won't be. I don't know. Maybe in my understanding, the radar jammer maybe will be a bit more expensive, and maybe okay, maybe for military use, yes. But actually, if you just want to do the to stop the Zoom operation, I think there had already been some commercial product of the RF jammer. You can do this. I don't think it can be as expensive as the radar jammer used by the military.
Okay, it is satisfied for you?
Yes, sir. Thank you, Mr. Hongbo.
Okay, thank you very much. Yeah. Okay, the time is already over. Yes. Thank you very much to Professor Hongbo and Professor Yoshio Yamaguchi. Yes, to share your knowledge, and I hope the participant here can, learn from you and continue the research. Yeah. Especially here is, I think, it's many young scientists and students that it is our, heritage for our future activity, especially in Asia Pacific area. Yeah. Okay. Yeah. Okay.
Maybe we need to take a picture for last moment before we.
Oh yeah. Okay. Let's take a picture. Yes. Could you open your camera? Yeah. Pak Wahyudi will take the picture. Yeah.
Yes. I will do. Thank you.
Yeah. Okay, we will
start now.
Yes, later on the magazine. Yes, our IEEE. Yeah.
Okay, first first page. Maybe Ms. Rika, can you help me for the second page?
For the second page, please smile to the camera. 1, 2, 3. Thank you. And then for the third page, please smile to the camera. Okay, thank you. And for the fourth page, wait. Okay, and then for the last page. Okay, thank you. Already done, sir.
Oh, okay. Thank you very much. Yes, and okay, our next tutorial is will be held. Yes, on March 24. Yes, please check the link on the website of the Aperture 2020.org. Yes, the next presenter is Professor Muhammad Aris Marfai. He will talk about the remote sensing technology for mapping because he is the head of the Indonesian information of the geospatial. And then Professor Akira Hirose from University of Tokyo. He will talk about, I think, the most hot topics right now about the big data of the SAR. Yes, it is big SAR data intelligence in INSAR and polarimetric SAR. And next, Professor Feng Shu, yes, from Fudan University of China. He will talk also, it is his hot topic about the deep learning as the applied in SAR imagery interpretation. Yeah, I think it's especially student. Yes, if you want to find the topic is the next tutorial is, I think is the best one. Yeah, so please also don't forget to join and always check the website of the Aperture 2021, and we will put the link of the Zoom and also the YouTube. Yeah. Okay. Before close this tutorial today, thank you very much to Professor Yoshio Yamaguchi and Hongbo Sun, and also the committee of the Aperture who prepare this tutorial, and the symposium is very hard. Yeah. I know we are very busy, but you share the time for us. Yes, thank you very much. And also Wahyudi Hasbi, PhD, he is the head of the president of Indonesian section, and also Arifin Nugroho Sang, he is the head of the Indonesian IEEE IAS, yes, JNJRSS. And also here is, I think it's Pak Agustan is the head of the Indonesian Society of Remote Sensing. Yeah, and also I'm sorry, maybe I cannot say one by one, but yes, I'm very appreciating to you to succeed this Aperture 2021. Please don't forget also prepare the abstract for the Aperture. Yes, and the deadline is next April 30. Yes, let's succeed our Aperture. Yes, because Aperture is I think it's not just my future, it's your future too. Yes. Okay. Thank you very much. And yes, I want to close this tutorial today, and keep healthy, and yes, safe with your family. Thank you very much, and bye bye. Yes.
Thank you.
Thank you.
Thank you, Prof. Thank you.
Thank you.
Very much.
Bye-bye.
Thank you.
Thank
See
you,
you
Prof.
next.
Bye-bye.
Thank you very much.
Thank
Yes,
you.
Thank you, Professor Sun.
Yeah.
Thank you.